Hello, we are Group 20461 presenting our project in animatronics for the TSa 2021 State Conference. Our animatronic is a frilled dinosaur, also called a Dilophosaurus. We based our museum exhibit off of a popular Hollywood movie to make the scene more interesting and familiar to the audience. The movements in the animatronic are the body, neck, frills, arms, jaw, jeep, and a waterfall. There's also compressed air released from the mouth to mimic spit. All of these functions are activated through a touchscreen in the front of the exhibit or an app on our phones.
For this robot and design, we used SolidWorks, which is a 3D CAD design software that we have all been learning in school and have received a lot of certificates for. We had a lot of fun designing all of these parts that are 3D printed, and they all turned out incredibly nicely. And I think my favorite part of this project was this neck joint here. We ended up redesigning this, or actually I ended up redesigning this almost 5 times. And in our final design, I ended up using what's called a planetary gear assembly, which essentially is you have one driven gear off of the stepper motor, we have 2 planetary gears, and then one huge ring gear that can gear down rotary motion in a straight line. And it was just so much fun to design and print, and ended up working incredibly well, so I'm satisfied. One of my favorite parts about this dinosaur is the body joint, which we actually ended up having a lot of trouble with because it had to tug such a large mass to give us about 30 degrees of motion. So what we ended up doing is hooking up a stepper motor to a 3D print belt. The belt was rigged so that it would spin the large disc slower than the stepper motor, so we would have more torque out of it. Another cool part about this dinosaur is the tail, which is also driven by a 3D print belt and a 3D print gear on a stepper motor, which was pulling it one direction, which bent each individual section inward, and then the other way, bending it back. This was all done through springs and through a bunch of different pins.
So basically what we wanted to do to make this as realistic as the movie is, we had a fully functional Jeep Wrangler YJ, which imitated all of the functions of an actual Jeep. It included back tires that rotate very fast, imitating it being stuck in mud. And following that, we had a fully functional front tire set, which rotated at a random pace according to our program that we wrote. The entire program was written around Lego Mindstorms, which was very helpful in this process. With the waterfall, we wanted to make it as realistic as possible. So what we did is we took a water pump from an aquarium and we used that to pump the water up through the system and get it back down and circulate to create an actual water flow. To make a more realistic rock texture to the waterfall, we used a joint compound, let that dry. We painted it over with some spray paint that had texture to it. This allowed us to create a very realistic looking waterfall that did its job just as we hoped it did.
So we wanted to use Arduino because it's a circuit board that we're familiar with. However, it has its limitations because they can only do one thing at a time. We took our inspiration from supercomputers, which have a unique property where they can actually send out multiple signals to multiple processors to do multiple things at a time. And they all run off one sort of mother microcontroller. In our case, in our supercomputer, our mother controller is the Arduino Do, and that sends out signals to 2 branches. The first branch is the user interface. And the user interface is a Raspberry Pi 4 and an ESP32. We wanted to make it user-friendly, so there's just a touch screen with 4 buttons that they can use to control the animatronic. The other branch is the actual physical motion, and that goes out to an Arduino Uno and a Cduino, and those are in charge of moving the stepper motors, the servos, and all other motions. This was tricky, sort of combining different powers because the stepper motors need 30 volts while the main motherboard only runs off 3.3 volts. So it was a lot of math and regulating voltage so we don't fry the whole thing.
So the frills were an interesting mechanism because there isn't a ton of things that look like they do and work in the constraints that we needed them to. They had to pop up fast and yet still be strong enough to withstand the forces. We also needed them to be as small as possible in order to be aesthetically pleasing. Finally, we also needed them to work within the movements of the other joints without getting in the way. At first, we used torsion springs to try and propel the frills, but that was a little too strong for what we needed. Instead, we opted for lighter straight springs that we just bent in the shape.